What's up, YouTube? Today I'm going to do section 2 for a previous YouTube that I did for section 1, and that's the 2024 January question 1, this conversion of industrial building to apartments. So if you want to see how I tackled the concept designs in section 1 and how I critically sort of evaluated the two, go back to my previous video. But if you're interested in looking at section 2 and how I've sort of gone through and presented my calculations, provided some drawings as well as a detailed method statement, hang around. Just to add to that, I do plan on doing a few more of these. So I plan on essentially sitting the exam this coming July. I was hoping to do it in January, but I wasn't really ready. So if you want to share the journey with me and just see how I'm sort of tackling these past papers, make sure that you subscribe, because I do plan on doing a few more of them more regularly. Before I go a little bit deeper into section 2 and what I've done, I had a look at the examiner's report, and there are a couple of things that I found a little bit confusing. So if you also don't, I'll just share what it is. So on the right hand side of my screen, I've got the examiner's report for the exact same question. If I was a student sitting this exam and I read this point here, omit from consideration the stairs and lifts, elevators, and atrium glazed roof and glazed elevation secondary steelwork. However, in the chief examiner has put here section 2C calculations, the lateral support for atrium and lift stair openings. So if anyone here sort of thinks that should be there, or if they're confused like me in terms of why that's there, just drop it in the comments, and I'm sure you'll help not only my understanding but anyone else watching this, because that's the idea of this channel, that we all sort of improve each other's understanding. So that was one thing that took me by surprise. The other thing was, if we just stay looking at this, section 2 clearly asks to include, not only, if we go back here, it says to omit from consideration this, which is what this here looks like. So why that's in there is a bit confusing. But what should be in here is your carbon calculations for each of your principal elements. And I couldn't see that, in this chief examiner's critique. So that was just something that I thought was interesting. But moving on to what I'd actually prepared. If we go back and look at the options that is in this review here, the one that I presented was pretty similar to option 1, the reuse of the existing steel beams and columns. So that, the idea behind that is just to reuse as much as possible, which is obviously a big factor in these newer, more recent IStructE exams as we tackle the climate emergency that we're facing and try and really reduce our embodied carbon. So let's get into this. I'm going to quickly go through my calcs, how I did the drawings, and my method statement. So if we come over here, the calculations that I've put together, the way I plan on presenting it is essentially just going through and looking at, for this particular scheme, we had the existing floor that we're keeping, so just a quick indication in terms of why that's okay, and then I'll go through and talk about the floor beams, the new column, lateral stability, the foundations, and some carbon calculations. So having a look at the existing floor, if we go back and I put it on the right hand screen over here, they give us the loads, the unfactored imposed load capacity of the existing floor is 6 kPa, and then we can see that the new floors, whether it's within the corridor or on the apartments or the roof, it is less than this. So I had literally thought it's appropriate just to put in a little one paragraph describing, okay, we're not changing the existing structure at all, because I'm leaving it as is. In fact, I'm actually adding a few more supports, because in my scheme I add columns along the corridor here. So 6 kPa is more than the loads being introduced, so no further calculations are required. Now I go through and do a column, and I know a lot of these calculations, like when we do them in the design office, they can be a lot more tedious than what I'm showing here, but I think the idea and what I plan to do is essentially just do some basic calculations, look at the tributary area, multiply that through for each of the floors, and then, yeah, I think it's a lot easier for someone else to actually understand your sketches as opposed to just a pile of numbers. So I would recommend have a sketch to sort of reflect what your numbers are showing, just because it's easier for anyone to pick up. Like if there was no picture there and we're just looking at that, that's a bit hard to read. But if we've got this here, anyone can look and go, okay, yeah, we're looking at a column here, that's a critical column, there's a tributary area, and there's my axial force picking up as we go down to the base of the structure. And there's my factored load here. What I don't have here that I should is the 1.2G plus 1.5Q. I should reference which standard I'm using, which is AS 1170.4. And then here, I've used a circular hollow section because, I mean, I'm a little bit lazy. There's no sort of like strong access with circular hollow sections, and they're really easy just to pick up what the compression is. So I've just said, you know, it's 3 meters because that's essentially the distance between the floors. And yeah, I don't have to worry about biaxial bending because it is a circle. So that's what I've done for a column. And you'll see with each of my principal elements, I'm just trying to do some basic calcs to show the demand, what the capacity is, and a couple of illustrations to reflect my reasoning. So yeah, that's what I've done for the floor, the existing floor, the new columns. If we come down here and check out the foundation. Now I know you can do a lot more calcs with the foundation, but again, I'm just trying to keep for each principal element 1 page. So my experience in design, and I'm sure a lot of you watching will agree that when you're designing a foundation, we size it for the bearing capacity, and then I'll do I'll look at punching shear, and then for reinforcement, I'll just allow for a degree of crack control, which is essentially what I've done here. Now, when we size for bearing pressure, I use allowable, so then that's why I'm kind of showing here the unfactored loads here. That's how I've sized this pad footing. Again, if you go back to my where do I get the allowable bearing pressure, I've got a video on foundations where I talk about, yeah, where they give us the site conditions here. They tell us that at this sort of depth, which is where my footings will be founded, you get the SVT end value for this profile. So that's where I get 500 kPa. I use that to work out what size footing I need, so 3.6 meters squared, we'll call it 2 by 2, will give us 4 meters squared for this allowable load here. So we know we're good for bearing pressures, we've got our size. And then for the depth of the footing, you can see here, this is normal in design, and I expect any examiner would appreciate that. Anyone sort of like reviewing your work, if you've done some calcs and you realize it's not enough, just a simple line through as you would in your normal design practice, go back and go, this is me here. I think I originally tried, what is this? This would have been a 500 deep. I'm allowing for 50 mil cover. I figured out that wasn't actually deep enough for the punching shear. So I increased it to 800 and then that works. So that's, yeah, we've sized our pad footing. We've got 2 meters by 2 meters and 800 thick. And then in terms of reinforcement, I've just allowed for a high degree of crack control because it's embedded in the ground. So that is up 0.6% reinforcement, which ends up being 1500 millimeters squared. And then we know an N20 is 314, times it by 5 is more than 1500. So N20s are 200. So that's how we've got my foundation. Now moving on, for the new floor, I used some secondary and primary steel work with some new columns as well. And I mean, you'll see it in my drawings, and some CLT, because CLT floor plate spanning 3.5 meters. So again, as I mentioned before, just some really simple calcs that we got here. I'm just showing the like a bending moment diagram of my CLT floor spanning in between the secondary beams, which are spaced at 3.5 meters. My moment is roughly WL squared on 10 for a one-way spanning system with multiple supports. Here is some basic loads that again I've just taken off the brief to get my bending moment. And here, and if anyone's got some, I looked forever to get some bending capacities and whatnot for CLT, but all of the documentation that I found was talking about how CLT was governed by CLT floor plates are typically governed by vibration and footfall analysis, as opposed to actually sort of like your traditional strength checks that we might do for concrete and steel. So yeah, if you've got some back of the envelope calcs that you think are worth knowing, put them in the comments of this channel, of this video, and that'll be really helpful. But in the meantime, I literally just plan on just showing span to depth, which is suitable for my 150 CLT. Here I'm using 150, we're spanning 3.5 meters, so yeah, my span to depth ratio is suitable for the CLT. I would have preferred to do a bit more calcs, but again, all the looking around that I did, I really just saw this commentary around how you got to check it for vibration, and there's no way that I'm sitting in this exam and doing some vibration calcs. There's just not enough time. So for my primary beam, in my opinion, it's not necessary to go through and detail all the beams. We're really just showing the examiners that we understand load pass and calculations and general principles. So I just decided to do a calc on the primary beam. I've used a 200, similar to my footing. I realized I had to actually upsize the beam, and I know we've got some height restrictions, but I think this is okay because my primary beams can actually land on top of the partition walls between the apartments. So that increased depth shouldn't be too much of an issue. So yeah, here I'm just showing the bending moment and shear force diagram of my primary 250 by, that's 150 RHS. And just some simple calcs, and it's got lateral supports at, 3.5 meters, so that explains where I'm getting my effective lengths from, my bending moment capacities, and my shear capacities. That is, so that's how I've designed the new floor. Moving on, the concrete wall. So this is essentially for lateral stability. It's, while it will pick up some vertical loads, the purpose of my shear walls are really for lateral stability. So here I'm doing a wind calc. If you remember from first principles, 1/2 rho v squared to get wind pressure. And I'm aware, maybe I got a bit lazy here, but I'm aware, in the Australian wind code, we've got pressure coefficients for buildings and whatnot. I've left those out and just assumed, I've just taken the wind pressure and times it by the area, because again, I'm showing that I understand, wind pressures and loads and whatnot, but in the space of this exam, I don't plan on going to the nth degree. If you think this is wrong, leave a comment, let me know. Maybe others will agree, but this is my battle plan at the moment. And then here we've got the load coming, the critical path. If you look on the right hand side on the plan view, you've got a lot more area here. So when I do my calc, I take wind going in this direction, which is, that's the total load there. I got that pressure, 40 meters by 21.2 meters high is that force. And then I divide it for the 6 walls, because in that direction I've got 1, 2, 3, 4, 5, 6 walls. So I end up with 183 kilonewtons per wall. That acts at midpoint of the wall. And then for the stress of the wall, if you remember, P on A plus M on Z. And as I mentioned earlier, I'm not really considering this shear wall as a vertical load element. I'm really just focusing on its lateral. So for that, this stress that I've got here where this guy is in tension, this half of the wall's taking compression. Yeah, we're really just looking at M on Z. So Z is just a function of the geometry of my core wall. So we're saying that's 7 meters this way, it's 200 meters thick. And then, yeah, essentially M on Z, I get a stress, which is here. And then I work out the area of steel that I need to take that stress. It's quite a long wall. I realize it's actually not that much area of steel for 500 MPa, which is the field stress on my bars. And then I just say min steel governs. So I choose an area of steel for essentially just some crack control, which is here I've used N16s at 300. So yeah, that's again just doing some calcs for the demand. We've got some wing calcs, showing some sketches to show that we understand load pass and what we're actually designing for, and then just choosing some sensible calcs to, okay, yep, there is steel that we need for that stress. It's not that much, so minimum steel will probably govern here. And then that's all I've got for my principal elements. Then finally, so for the calcs, I've got my embodied carbon calcs here, and this is, I actually haven't finished, as you can see here, but essentially I looked at the IStructE guidance and I've actually got it up here. It's a little bit, in my opinion, maybe it is what it is, tedious, because if you look at the embodied carbon calcs, it gives you all the concrete unreinforced. And there are no piles or substructures or superstructures that are unreinforced. They're all going to have reinforcement. So this must be because they're trying to be more accurate, because it obviously depends on your reinforcement rates. But I think for the purposes of this exam, it would be okay to get a more sort of approximate figure. Bit more of a crude number. So I found some other numbers here. I wouldn't quote this for now because I literally just picked them up like half an hour ago or so. But these embodied carbon factors, instead of in the unit of kg per meter cube, which I believe these ones here are, per kilogram, sorry. Yeah, this one here is like a function of area. But essentially, yeah, what I plan on doing for my embodied carbon calcs is really a simple table like this, where I look at my critical elements. I got my shear walls, I got my CLT floor plate, and my foundation. I've got an embodied carbon factor here, which, yeah, you can bring into the exam as open book, and then you just essentially work out your total. In this case, it will be area, so the total area of my shear walls, my CLT floor plates, and my foundations, and then multiply the two, and voila, that's how I'd get my embodied carbon. But I haven't finished that, and yeah, that's essentially just showing you my process. Now onto the drawings. What I did here, I've got a foundation plan, something that I've personally been keen on learning, because in real life you're never going to have to draw a detailed drawing. You do sketches by hand, but not drawings. I've personally wanted to learn how to use Tekla, so I've decided to create my drawings using Tekla as I prepare for the IStructE exam. Now, obviously, in the exam itself, you're not going to be able to create your drawings using Tekla, so I'm not saying it's the best approach. For me, it's just a fun way to learn how to use Tekla and sort of, document your own designs in practical fashion. So here is essentially my design. The yellow slabs here are my CLT floor plates. The green columns are the new columns that I've put in, and the red columns are the existing columns. You can see the windows that we've had to adjust. Anyway, so this is essentially what I did to create my drawings, which is a fun way to learn Tekla, but not necessarily the best way. So I would first draw a foundation plan. That's what we got here. If you remember from the brief, they didn't actually tell you what the existing footing details were, which is essentially why I have this note here saying, yeah, I haven't drawn what the existing footing details are because I don't know what they are. And I've just left a note here saying that. So the footing details that you see here, the strip footings around my shear walls and my pad footings around my new columns that we sized before, which are 2 meters by 2 meters. Yeah, my first drawing here. Moving on, so we've got the existing floor, which looks like this, just that steel beam and the precast slab. So that's what that looks like. Then one drawing, plan view, showing a new floor. I should say something like typical here, but if you remember my concept sketch before, I added some new columns along that existing corridor, just equally 8 meters, so sort of equally spaced in between the existing columns, and that way I don't have to sort of introduce any new loads onto the existing structure, because yeah, we don't know what the footings are, so I don't think it's a good idea to load up the existing columns when we don't know what they're sitting on. So this is, yeah, the steelwork, the secondary steelwork that you see here running left to right, the primary steelwork, the RHS running up and down. And then my core walls, 200 thick core walls, look like that. The existing brick masonry facade out here. Yeah, so that's a typical floor. If we move to the next page, we've got the south elevation. And remember, we had those geometry requirements on the windows where they had to be 1 meter above the existing, 1 meter above floor levels, 1 meter high, 2 meter wide, and then they're sort of like 2 meters apart. So I've just dimensioned that and then drawn those on one south elevation. And then again here, I've just shown the minimum height requirement, if I'm not mistaken, was 2.3 meters or thereabouts. Yeah, a clear floor to height requirement 2.3 meters. So obviously that's pretty important. So I've just dimensioned here, showing how I maintain that between the existing and the new. So the existing is, they're a bit luckier. If you're on the existing floor, you get an extra 200 mil. So I got 2.5 because that CLT is a bit smaller, a bit shallower than the existing precast floor. The existing precast floor. So yeah, you got the 2.3 meters clear height there. Then I've got a section going along grid B. So actually, what I should have really done, yeah, it would have been good to do something along these lines. Show a bit of that. But whatever. So I've got a section here. That I draw here. And yeah, that's really just showing there's too many marks here, but that's kind of just how technically I output it. And you can see here, I got my pads, we've got each of the floor levels here, and then you want to add a couple of the critical details. So a critical detail that I thought here was that new column that obviously has to start and stop between each of the existing beams. So I've just added a section here, and this probably isn't enough detail, but yeah, my column essentially comes down and lands on that existing beam, and it's got an end plate and some stiffeners onto that existing beam. So there is a drawing. That's the extent of my drawings. Some critical details, 2 sections, one showing the elevation, another section just showing grid B. Then I show the new floor, I show the existing floor, and foundation plan. Then if we go back to what the question actually asked for, I feel like we've done our calcs, we've shown our drawings to a sufficient level of detail, and now we're going to prepare a method statement for the safe construction works. So if we come down and look at the method statement that I've prepared, and again, if you think I've missed anything here, just drop it in the comments so myself and others following along can learn and share each other's thoughts. So I've broken it down to these 7 primary steps where I talk about preliminaries, which is essentially just setting up a site, putting up a fence and whatnot, which happens at literally every construction site, and some groundwork. So again, I think for the method statement, if you read the examiner's report, they probably don't want too much of this stuff that can be applied to any site. They really want to see that you've thought about this particular scheme. And I can't see it being beneficial just copy and pasting the same method statement onto whatever design that you've got. So for this particular method statement, preliminaries, you kind of have to do that, but groundwork. So one thing that I obviously have to do before I land any new columns is to excavate and penetrate the existing ground slab and provide some new pad footings there, as well as some strip footings for the new shear walls that I'm putting up. And then after that, I would go talking about the substructure. I would pour those pads and strip footing down for my superstructure. I would talk about bracing the elevations for the new penetrations in the slab for the atrium and proposed lifts. Again, it did mention something about omitting that, but anyway, I've got that there. Then essentially penetrating the slab for that new atrium and the lifts, and gonna have to penetrate the existing slabs for the new columns that I'm going to be putting in. Then after that, I'd pour my core walls, try and get the lateral stability system in, and then install my steel work, being the columns, and then the beams for the new floors, and then the CLT floor plates, and then finally I'd do the cladding. Just flagging here that I think I flagged it in my section 1, but to satisfy the requirements for the window spacing, you can't actually use the existing windows. If we come here, 1, 2, 3, 4, 5, 6, 7, 8, we got 8 windows going up. And the existing facade, I don't think I had that many windows. No, 4, so the windows essentially have to be taken out and new ones put in. So I'll probably add something around here about like some temporary work that will be required to support that whilst you replace the old windows and add new ones. Then finally, remove your temp propping on your elevations now that your shear walls are in. Then finish it up with services and finishes. So that is section 2. I've got my method statement, I've got my drawings, and I've got my calcs for my critical elements. So if you want to see more of this, make sure that you subscribe. If you liked it, give us a like, and if there's anything that you think I did wrong here, feel free to leave a comment and I'll get back to you. Thanks.